Welcome, and this is our fourth lectures on this series about the neural differential equations and its applications in complex systems. So if you miss out the another three talks, that you can find out the two of them on our YouTube channel, because the second one actually is the more recent result, and he didn't give us permission to film. But the good thing is that Daan also give us the permission to film this, and if you would like to go back or share this talk with your colleagues, please feel free, and we will upload to our YouTube channel. So today we are very happy to have Professor Daan Crommelin here, and actually he will be the only one that will be in person on this series, and so that's because this field is so new, and so far we only have speakers from US, especially from California. So some of you will notice that we already hosted 3 dinner events, and the next one will be dinner events again. So today, please cherish this opportunity that we have a Daan in person here, so you could have some nice interactions with him. So let me introduce Daan first. Daan is a senior researcher in the Scientific Computing Research Group at the CWI, as we know, that's the National Research Institute for Mathematics and Computer Science. And he also is the professor at the Korteweg-de Vries Institute for Mathematics at the University of Amsterdam. And his work, and from his title, you already can know a little bit, his works on stochastic and computational methods for multiscale systems with applications in climate science and energy systems. And I know them, and because we also had I coordinated one with a big consortium and meet a lot of brilliant mathematicians and also climate scientists. And this is my first time that I could get the opportunity to hear your work. So please, floor is yours. Thank you.
Okay. Thanks for this introduction. I think for the invitation and the opportunity to present some work that I pursued with a whole bunch of colleagues, as you see here, over the last few years. Yeah, so let's dive in. You've seen the title by now. This slide has been up for a while. Is the recording going okay?
Yeah.
Okay.
Yeah. No problem.
So, first of all, so the title was model closure, and I'm not completely sure if that's really obvious to everyone what is meant by that. So I have 2 slides to, well, kind of summarize and motivate why model closure are important. So it's really about representing unresolved processes, or more broadly, model error in usually computational models of large-scale dynamical systems. So one example is climate modeling. On the left, you see, you can recognize Earth there, and a computational grid for the atmosphere model. It's a sketch of that. Of course, it looks perhaps it has already significantly high resolution, but of course we know that the model boxes are still huge, and within each of those boxes, still a lot of processes take place that can't be captured by a model that covers the entire Earth. And here on the right, you see a figure from the latest IPCC reports. On the vertical, it shows for all kinds of IPCC models, or CCSS models. It shows the horizontal resolution of atmosphere models. You see kind of well, it goes roughly from the order of the extremely high ones, 25 to 50 kilometers, down to 200. That is way too coarse to resolve. For example, cloud processes and convection. Right, so that needs those processes in most models still need to be parameterized. So you need a model closure or parameterization. A different example that I hope to get to towards the end. This is from computational chemistry. Here you see, and I can see the picture is a bit dark. In that box, you see 2 red particles that form a dimer together, and that's so they have particular interaction potential that you see on the right, and it's immersed in a solvent. right? And if you want to understand the dynamics of that dimer in detail, to simulate it, there will be solving particles that interact with the dimer particles. Of course, it makes it very computationally expensive. So there's an interest in trying to sort of essentially no longer have to resolve all those solving particles in your simulations and only the effect of it on the dimer particles. Right? And then, of course, to do that, again, you need a closure or parenthesization, right, to represent the effects of all those solving particles. So that's that is model closure. Also, especially in the abstract ocean and climate science domain, is better known under the term parenthesization. I'll use those words a bit interchangeably. Okay. Yeah, the little analytical example to show this is come from fluid flow, so it also applies to abstract flow. Very simple example, two-dimensional fluid flow. You see the partial differential equation in the upper left. Right? This is a particular form of the Navier-Stokes equations, and it has this nonlinear advection term that I show at the bottom. Right? It's formulated in stream function vorticity terms here. And the thing is that if you somehow coarse grain this, you see, so you have a sort of high result field on the left, and you say, you know what, I'm going to do what's random decomposition. So you have a field that represents all the larger scales, and then everything that's left, and small scale features. And if you do that, then you say, well, I'm mainly interested in the large scale fields. So what's the partial differential equation for that? So you get almost the same thing as we had on the previous slide, except for this extra R term here. This term stemming from the subgrid scale stresses. Right? And that is unclosed because, as you see here, strictly speaking, to represent that in full, or exactly, you would need the full, so also the small scale vorticity field to be able to do that. And of course, that's something you don't typically have if you only resolve the larger scale. So somehow we need to parameterize this term R in terms of these larger scale result fields, psi bar and q bar.
Don't you want any stochastic terms in your equations?
Well, so that's I'll get to that later. Sure, I mean stochastic terms typically pop up. So I'll get to that in the second part of my talk. Okay, it's more the stochastic setting, stochastic parameterization. Okay. Okay, let's go to the machine learning. Of course, I mean this problem of model closure characterization is people know about this for a long time. This is of course it's notorious, and as you can understand, over the last 10 years, people have jumped on machine learning to do that. Right. So this mapping. Right. Let me go back one slide. In context of this little example, so this parameterization, right? So given that you have your coarse, so your large scale vorticity and stream function fields, try to find R. Okay, that parameterization. Of course, with the expressivity and all the power that machine learning tools have to essentially do function approximation. That made it kind of a natural way to go to at least to try and explore that can be used for parameterization and model closure. Here you see just some snippets from paper titles, very selective. I mean, there are hundreds, maybe more papers right now trying to do this. As I could have added many slides just showing these titles. Here you see a couple that come both from the climate science and from the computational fluid dynamics domains. Okay, so a bit more, abstractly, what are we looking at? So I'm going to focus on a set of coupled ordinary differential equations. Is that let me get this pointer here, right? So the one here, u over dt equals f of u, right? It's a set of coupled ODEs that can come principally from spatial digitization or Vidi, but can also have some other source. And the closure that we add to that, here you see it's right, it has the form of a neural network. But neural network closure, and that means that sort of collectively, the right hand side of this, you can say, well, it's this is a neural ODE because it's a differential equation where the right hand side is expressed by a neural net, right? And this was introduced some 5-6 years ago with NeurIPS in this paper by Chen et al. That maybe has already featured in previous talks from this series. Okay, now, of course, the question then is how do you train that? If you have a neural ODE, how can you train it? So I'm going to use the general notation, right? Whether G is entirely a neural network or it's a knowledge-based or physics-based part with an add-on that's a neural network. It's a closure parameterization. It doesn't really matter too much for this general idea. So you can train this in several ways, right? And so what we did in a recent paper with a bright student that we had in our group is to compare two approaches for training. As you see here, one is we try to fit these, right? You see in the, let's say blue is a trajectory of the full model, the trajectory that we'd like to capture. That's given by the data, effectively, right? By the model, it would be a perfect representation of the system. So what you can do is see if you can capture the derivatives at different time points to the best extent possible, right? So minimize errors in the time derivatives. So we call it derivative fitting. Another way of going about this is saying, well, I'm not so much interested in these instantaneous errors, but in the error that accumulates if I integrate this dynamical system over a short time span. Right here, you see this starts. So let's say that's the dashed line here. It starts with the same initial condition, let's say the exact system, and then of course over time the error grows. And of course, that's another error that you can try to minimize. So that's what we call trajectory fitting. Right? So minimize errors over model trajectories. Okay. How does that go? So derivative fitting, in a way, is relatively easy compared to the other one. Because, right, okay, so you need the data, of course. Right, either you have these time derivatives as part of your data, if not, you can approximate it, which it introduces some error, but okay. You can approximate it with finite differencing in time, right? Now, given those data, the loss function is quite straightforward. Right, it's the difference between the time derivative of the reference data and the time derivative that we get if we feed the states of the reference data to the neural net, right? So the right-hand side of the equation. Right, and you can build an L2 error from that, so mean square error in this particular way. That is the loss function then. Right, so that's the object that we want to minimize in the derivative fitting.
But can you explain your notation a little bit? Because what G is a function and theta are the parameters that you're fitting or something? Or?
Right. Yeah. That's it. That's.
But you never explained it.
Yeah, sorry about that. It's indeed. So theta are the parameters of the neural networks, right? So here the trainable parameters of the neural network.
But how do you define G, the function G?
The function G is essentially a shorthand notation for what I write here. So that's what you see here. It's just so it's a full right-hand side of the ODE.
Yeah, but is that a prescribed function with parameters, or what is G?
G is, well, it can be either. So either can be in its entirety a neural net, or right, because we're talking about model closure, it can also be a part that's sort of prescribed because it derives right away from physical principles, and then added to that a neural network that acts as a model closure. Right, so that would be the situation here, right? So in that second situation, G would be sort of the sum of these two terms. So the full right-hand side of the ODE.
Yeah, but for you it's maybe clear, but what is a neural network in this sense? How does it represent the function that I'm interested in?
So the neural network, well, so I think of this as a mapping from the space of in which U lives, right, which would be a subset of RD to RD itself, because it's the right-hand side of the ODE. Right, so it maps the states to a term that is either the full or part of the temporal derivative. I
So
don't know
I
if
have
that makes
a
it
neural
clear.
network with U as an input, and it gives me an output that depends on the zeta parameters, and I'm fitting somehow
Exactly.
these parameters.
Yeah. There was a question back there.
No, I see that you use spatial discretization. So my question was whether the F that you have there is just a function of U, but or also of its spatial derivatives. But if you make a spatial discretization, then obviously that doesn't really matter.
No, that's I'm considering this in the sort of spatially discretized setting. Yeah. Okay, so back to derivative fitting. Right, so we have this loss function. That's an L2 error, and then the training of that. So for the training, we need the gradient of that loss function with respect to the parameters that we want to train over. And with this particular loss function, that is sort of relatively straightforward, right? Because the neural net, right, that is in G, is right there in the loss function, right? So we can compute this gradient fairly easily, right? And well, what you see here, the gradient of G with respect to the parameters is just the gradient of the neural net with respect to the parameter. So then we can train that relatively straightforwardly. That's different in case of this ideal trajectory fitting, right, where you want to minimize the error of a trajectory over a certain amount of time. So the idea there is that we integrate the ODE, right, from some starting time t star to end time t star plus capital T, right? So the initial condition we take from the reference data, and then of course so we compare the predicted trajectory, right, predicted with this ODE that involves the neural net. So we compare that predicted trajectory with the reference trajectory over that time interval, right, and then right, and compare that in sense of right to compute the error of that. And of course, then you do that with a lot of different initial conditions. And of course, one open question is how do you choose that capital T? Right, so the length of those trajectories. Right, that's not obvious. I'll say a little bit more about that later on. So the loss function formally, at least that we consider, looks like this, right? So again, it's an L2 error over these trajectories. So we start from a whole bunch of initial states, and then these trajectories, of course, have a certain time length. So you sum over all that and look at the total L2 error there, right? And now what's complicated here is that this loss function no longer depends directly on the neural net like it did with the derivative fitting, but now it depends on implicitly on it, right? It depends on the ODE solver for this that produces this predicted trajectory, right? And that makes the minimization more complicated. I'm not going to say too much about that. So perhaps this is already featured in previous talks. Right, so this the gradient of the loss function with respect to parameters is less straightforward than in the derivative fitting case. Well, there are two approaches that people are pursuing to do this. Going under a whole bunch of different names, but we've adopted these names: optimize and discretize, or discretize and optimize. In this first case, you compute an approximate gradient by augmenting the system of ODEs using the joint methods. Okay, so that's one way of doing that, and then you solve that, right? That augmented sets numerically and gives you an approximation of the gradient. That is one way of going about that. The other, discretize and optimize, is really sort of back propagating through the solver for the ODE. Okay, so you differentiate through the numerical solver, and it gives you an exact gradient. Right, an exact gradient of the time discrete system, because that in the end is what the ODE solver produces. Right, and this last approach goes under different names: embedded training, unrolling, solving the loop. People have used different names for that. Okay, and here's this is a table from the paper on different properties, different requirements that these methods have. Maybe most important for now is the fact that, so this discretize and optimize is nice if you get the exact gradients. Drawback is that you need that ODE solver to be differentiable with respect to the parameters. Right, and that is something that people can sometimes in a whole bunch of cases can sort of extract their software to do that, but it's not always, and it depends a little bit on the ODE solver that you use. Right, for instance, if you have a legacy code that is involved there, it's not so obvious how to do that. Okay, I didn't want to stick too long with more the way in which you train this, right? This trajectory fitting in much detail. So let me go to an example. So this is what's called the Kuromoto-Sivashinsky equation. It's a one-dimensional PDE on a periodic domain, and as you can perhaps already tell from this figure here, so that's chaotic behavior. So what we try to do here is first we produce data at high resolution, and then try to essentially reproduce the behavior of this system with a discretization that is much coarser, and then with a model closure as an add-on to make up for whatever is left out. Okay, there's some right. So again, this is the setup that we now have, right? So this apple view comes from discretization of the PDE, and then we have the neural net sort of add-on as model closure. Yeah, some details about how we do that. For finite volume discretization for for the spatial discretization, and there is the fact that this Kuromoto-Sivashinsky equation conserves momentum. Right, so how can you build that in your neural network model closure? Well, the way we did that here is by using a kind of a flux formulation. Right, so the neural network closure effectively produces some things you need to take the flux of, and that is then what is added as the closure term. Right, so that's that makes it possible to ensure momentum conservation from this model closure. Okay, and now some more when you conclusion neural net. I don't want to go into the details of the architecture of these neural nets. I think that's not the main point here. Just let me go on. Here you see one example. So of the error growth, where I use trajectory fitting to train the closure. So over time, this is expressed in number of Lyapunov times. So at about 4 Lyapunov times, at some point it starts to grow rapidly, and the prediction is no longer useful, right? If you want to use it as a point prediction. Okay, so this is kind of typical behavior error growth that we see. Okay. At the next slide, we're going to see a little table that sort of quantifies the performance of these different training methods, right? So the derivative fitting and the trajectory fitting. And it's going to express it in terms of the valid prediction time, which is a way to quantify up to what time the prediction is still reasonably accurate. Okay, and so you set the thresholds. We say, well, whenever the difference, the distance between the predicted and the reference trajectory becomes too large, then we say, okay, then it's no longer useful. So when the point where it crosses that threshold, right, the time moment that we call the valid prediction time, and then this is averaged, of course, over a lot of these trajectories. So this is the whole table. Let me not discuss in full. We just draw your attention to, of course, these two. So this is the average valid prediction time for all this for the various training methods. What you see here is that sort of the best performing is the discretize and optimize. That was the method where we compute the exact gradient, right, with this back propagation through the ODE solver. Right, so that's the largest VPT, right? So large is good in this case, the larger the better. So it performs better than the optimized and discretized, also better than the derivative fitting. Right, so derivative fitting, that number you see up here. For this particular example, so Korteweg-de this derivative fitting actually still performs reasonably well. We have another example that I haven't included here on doing this similar study on Burger's equation, and there the derivative fitting performs terribly. There, the error grows very rapidly there. Maybe for me the most striking thing here is that in both this and this pair of results, what performs best is the situation where these trajectories are not too long, right? So you see two cases, so the shorter and longer trajectories, effectively, right? You remember that capital T that I said you have to somehow choose for this trajectory fitting, right? Over how long trajectories are you computing the error? So intuitively, you might think, okay, the longer the trajectory, the better the performance, the longer the valid prediction time. And what we find here is that is not the case. It's the shorter trajectories that perform best compared to the longer ones here. Right, so it's a bit counterintuitive.
What's the coarse ODE, the first line of the table?
The coarse ODE is where we don't use any closure at all.
Yeah.
So you just have the discretized PDE without trying to make up for the subgrid scale error.
Can we then somehow evaluate how good the improvement is? If you go from say 2 to 7 in
these are well, so here it's expressed in terms of this valid prediction time.
Yeah.
Yeah. I mean, it depends a little. I mean, you can formulate all kinds of criteria, of course. But this here, it's the VPT.
So, sorry, are these results also consistent over different types of neural network architectures? Because you said wasn't so important, but
yeah. So here the sort of neural network architecture was sort of kept the same over these different setups.
okay.
But yeah, I mean, there's the whole zoo of different architectures, of course.
Yeah,
you
sure.
still also explore and see if you can improve on that.
Yeah, okay.
Okay, so well, here's a figure that's well essentially shows the same thing, right? So the growth of the root mean square error over time for these different methods, right? And again, it's the discretized and optimized with the not too long trajectories that becomes best here. Right, so consistent with what I showed on the previous figure. But let me go here. So here are now two theorems of trying to give something of an underpinning of what we just saw. So why do the longer trajectories, right, the trajectory fitting with the longer trajectories, why does that not perform better than the shorter ones? So there's some other, so people have observed in other studies that maybe you are able, and that's what this slide is about, related to the derivative fitting. There are examples of cases where people manage to fit these derivatives with a neural network very, very accurately. And then they put it in their solver, and do sort of forward simulation, right, with this neural network based closure, and it performs terribly. Sometimes the system even becomes unstable, sort of blows up. But why is that? Well, this theorem, which is essentially nothing more than an old theorem from by Heyer and others on numerical methods for ordinary differential equations. This gives you some idea of where that comes from, right? So what this essentially says is, well, okay, if I can fit, right, if the error that I make on the right hand side of my equation, right? So here's the time derivative, and this is what I fitted to it, right? The g. If I manage to get that error below epsilon, over time I still get exponential error growth. Right, so even a very accurate right hand side, right, thanks to a very successful fitting of your neural net, eventually your errors are still going to blow up. And there's something similar for the trajectory fitting. Here this is the error that's made on a one time step ahead prediction. Right, so I feed my reference data states at time ti to the right hand side with the neural net. Equal one time step further to ti plus 1, and I compare it to the reference data I have there. And if I do a very good job on that, so error smaller than epsilon, effectively still exponential growth. Right, so k is the time index here. Right, it still blows up. Right, and you can extend that to, so this is just a one step ahead prediction, and you can generalize this to multi-step ahead predictions.
Is exponential growth related to having a positively upward exploder?
That's not a requirement here. No. No. Of course, I would add to the problems. Yeah. Yeah. Another question.
So would adapting your loss function to include this temporal component, would that be meaningful?
Well, in a way, that's what we try to do with the trajectory fitting, right? Because there, the error is, you compute the error over the time interval. Right, and yeah, what's difficult there, so let me maybe go back a couple of slides. Right, so this is the log function, right, where we go over a number of time steps, right? So ti, where I runs from 1 to some capital NT. Right, so effectively go from time 0 to time capital T and compute the total error over that. Right, so it is sort of, well, distributed in time, if you would. And what appears to be going on here is that, of course, if the error grows that fast, then the largest contribution is loss function. This loss function is typically coming from the final time points. right? So we've also experimented with trying to suppress that, right? Where you put some kind of a weight that decays over time, but that didn't really improve things.
Yeah, this question.
Yeah.
Yeah, just want to ask, to what extent do you think this is this problem actually looks to me a bit like the classical overfitting problem of neural networks, right? You seem to overfit and then basically use the neural network to do something else, and then basically it blows up. So the question that I have is that there's of course classical ways to deal with overfitting, basically to constrain to keep the parameters of the neural network small, for example, or I don't know. Have you thought about that direction? Or
No, of course, there's a lot of the strength of neural networks come from the fact that it is, I mean, there's over parameterizing. You have huge numbers of parameters, and it can still perform well. This was, I guess, again, counterintuitive years ago for people to see this. I mean, you have so many parameters, how can you possibly fit that? And in a way, you can, but it still performs well in many cases, right? So whether it would help here to reduce the number of parameters, to sort of constrain the neural network further, because I doubt that, because that problem of error growth isn't going to go away with that, of course.
Because I know results where basically people have achieved very good results with very simple models that you wouldn't expect, right? You can fit a huge model to these things and then basically generate biased results with it, right? And then basically if you make the model easier, you have it because maybe the model then basically understands the trajectory better, right? Then you might actually prevent certain type
of course,
Just thinking about that, yeah.
No, it's a good point. I think, I mean, I see this the sort of the phenomenon that's a lot of the results or the research in this direction is banking on is precisely the fact that you can over parameterize and still perform very well. So that's and sometimes I get asked the question, why don't you make a larger network with more parameters to do better? Right? Which is a completely different direction, precisely because of this reason. Okay, when you typically want to over parameterize for neural nets. Yeah.
Good question. That's it.
Okay, then we go to the in the last 10 minutes or so, go to the last topic. So, right, this going stochastic. So far, what I've discussed is all about what I see as deterministic model closures or parameterizations. I want you to train your network. If you fit it the same state twice, or if you give it the same input twice, it will give you back the same result twice. Now, a completely different point of view comes from this say research line that's been pursued for over 20 years now to in the Atmosphere Oceans modeling community to make closures stochastic, make them random. Tim Palmer has been a particularly vocal proponent of that, and I guess one of the first persons to push this idea in the first place. So you see this is an overview paper from a number of years ago. Whereas next to that, so it's a stochastic point of view, it's the data-driven point of view. This is something I started working on already quite some time ago. This was all about, this really work about fitting stochastic processes. This did not involve at the time any machine learning. And then of course, data-driven, right, the deep learning, which is what I've discussed so far to some extent, came into view, what is it, 5-6 years ago. So you see, this is one of the earliest papers on pursuing this from Stefan Rask and others. So of course, it in a way it begs the question. So can't you bring these things together, right? You want to go stochastic, but also want to use machine learning ideas in this. So let me say a little more about this. Now, this is sort of the idea that's in a nutshell that I've pursued for some time now. So we're going to go to a discrete time setting, right? So this is now the system that I'm interested in. I have a mapping from xj, right? J is the time index, to my next state, and to do that, I have some capital F. That's for embodies all kinds of critical knowledge, right? So essentially, this comes from a discretized Vidi solver, right? Discrete in space and also discrete in time, and then I need an add-on, right? So my model closure. Now, the stochastic model that I would like to use for that is the following: given the current and past states of both the state X and the residual that I have here on the right hand side. Given the current and past states of these two things, so X and J, for the next time update, if this is truly stochastic, I have a probability distribution. This is not a single state, but I have a distribution, and I want to sample from that. I want to sample from this conditional distribution. Now, the distribution, and typically we don't know what it is. Right? Of course, we can try to fit it, but in a way, to me, that feels also needlessly complicated because I'm not interested in the distribution. I just want to sample from it. So sample from this distribution, and one way to try and do that, to approximate that, is by bootstrapping, by resampling. And so given the data, I sample from this distribution using some form of bootstrap. Right, and there's, well, one way to sort of formulate that a little bit. This idea relates to all the work on the local Markovian bootstrap. In hydrology, people come up with the idea of nearest neighbor resampling. It's a bit similar. So essentially, the idea is, okay, I define a feature vector. In this case, sort of for ease of presentation, just consisting of all R and J from the current time down to time J minus capital J, right? So there's memory dependence here, memory depth J. And when I integrate, sort of step forward in time, my reduced model with parameterization, right? I compare the feature vector that I have for my reduced model. I compare it to my data, all the feature vectors that I can extract from the data. And whenever it's close enough, I get a set of from all those feature vectors close enough to the current one from the reduced model. I get a whole bunch of, say, time updates for R for my data from observations, and I randomly sample from that. That's the form of bootstrapping that I use here.
Yeah. I understand that Rj plus 1 is fixed by the number of previous vectors. In physics, you would call that a random choice, but a memory kernel.
Yeah, so this involves both memory and random. Right? So memory comes from the fact that these feature vectors here have memory. Yeah, right. Yeah, and the fact that it's still random because I take a random, so I don't take the expectation of this set. Right? I just sample randomly from it.
Oh, I see.
Yeah,
So
we
it's
would call it call-up noise, right? It's not white noise, but call-up, because it depends on the previous history, and it can be even
it's non-Markov.
Yeah,
it's no more exactly. Yeah, it's not. It's
call-up noise.
It's even worse than the color, I'd say. Of course, it could be red, but then that can still be Markovian. But here it's even non-Markovian. I mean, that's at least the setup. And that follows, I haven't put that here on the slides. So there's sort of motivation for that coming from the framework of Moritz-Sanzig theory, where people have
It's even multiplicative. It can be multiplicative noise even, right?
Yeah.
Because it depends also on your x's.
Yeah, exactly. But it's because this allows for a lot of characteristics of that process R to be included here. Right? I'm trying to impose as little as possible, and you can do that exactly by bootstrapping. Right? This is just what the data gives me. Yeah, maybe a little illustration of how that goes. Let's go through that quickly. Okay, yeah. So here in blue, I have an observation time series, a long one. This is what the recent, say, part of the most recent part of the trajectory for my R that I have with the reduced model. So what I then do is look in this data to find those stretches, those time intervals where the trajectory looks most like what I have here. Let's say these are the 5 that look most like the one in red. So I sort of line them up. So here you see them. Those 5 blue ones, all of them, of course, have a next time update. So what I then do is to continue the red one here, right, for the reduced model, I just randomly sample one of these 5. Right, that would be what it comes down to. Right, so well, anyway, so do this one, any of these 5. Again, it's different from saying, okay, I'm going to take the expectation over all these end states. That's related more to say the idea of optimal prediction as proposed by Alexander Turing, but this is not what we do here. This is really random sampling. That can be done in various ways. I see I'm starting to run out of time. One very straightforward way is by binning. So we just bin everything. Right? We bin the space of the feature vectors. And I say I'm going to look where the feature vector of the reduced model in which bin it sits. And then I take from my observation data all the same feature vectors, all the feature vectors in the same bin. Okay, here's one example. Right here, I say the feature vector is one-dimensional. It's here on the horizontals. I have all these data points. So this is just discretizing. That's it, right? My reduced model, I just find in which bin my model sits. I have a whole bunch of points and I sample one of them. It's as easy as that. And that can work well. So we have in this older paper an example with the stochastic heat map model. But I'm saying already, so I want to show that molecular dynamics example where you also use this method. I'm warning you, there's going to be critical dimension if the dimension of the feature space becomes too large. Because binning a high dimensional space, I mean, it's very rapidly you run out of data. There are just too many bins for the data that you have. Right? But that can be partly solved again with machine learning. Okay, this is that one example. I have a movie, but I'm going to skip that. So this is what I already showed, this figure. The main thing is that we have this interaction potential between the 2 dimer particles. And that leads to say, metastable states of the dimer. Right? There's the open state and the closed state. The closed state are close together and the open state are further apart. And then due to all the interactions with the solvent particles, you get these switches from the open to the closed state and back every now and then. Relatively long time scales. Okay, that's so if we look at that model in full, right, so the dimer and the solvent particles, right, that can be described with this Langevin dynamics sort of set of equations, right? These are now SDEs, or there's some noise here. If we reduce it and we say we're only interested in the dimer particles, we get this set where J, right, is value 1 or 2 because there are 2 dimer particles. And again, we have this R quantity, which effectively contains all the interaction with the solvent particles plus the noise. They're all in this, what I call this auxiliary variable R here. And so again, we need to somehow come up with a model for R, right? So again, it's a problem model closure. So we did this with the binning. Get this binning sort of resampling by binning. Here you see some results. On the left, right? So these are particles in a periodic box. This is a larger box, so it's lower density. This is a smaller box with higher density. What you see with sufficient conditioning, right? So if the feature vector is sufficiently rich, you get a very good reproduction of this bimodal distribution of the relative distance, so the distance between the dimer particles. Right? Which, of course, the fact that it's bimodal relates to the fact that it is is metastable. We have the open and the closed state. So we capture that. We capture also the time correlation between these the time correlation of that distance. So it works nicely with the smaller box, the higher density, using the same feature vectors as here. The results are a little less convincing. So for instance, we can't capture the benchmark, right? So the fully resolved model results, we can't capture them fully. Same for the, this is the distribution. This is again, time autocorrelation of the distance. So here it worked less well. However, if we enrich that feature vector further, right, we can do that. Again, we can capture this metastable behavior. So here again, the distribution over these different states is well captured now with sufficient elements in this feature vector. And in particular, what I want to show here, this is the first passage time distribution, right, for the transitions between the closed and the open state. So it's a difficult one to capture, right, because this takes place on longer time scales. It's really about this switching between these two metastable states. What you see here is that also with this enriched feature vector, sufficiently enriched feature vector, we capture the distribution quite well. Right here you see the mean FPT, and in the last case, it's very close to this up to these digits, the same as what we find in the reference data.
Can you determine the noise correlation function that you need somehow to reproduce the best result?
The noise correlation function, you mean from the noise that goes into the Langevin dynamics?
No, this noise of the effective model. So what is your effective noise that you have to reproduce your best results?
So that is, well, it's sort of, it's a bit implicit, right? Because it comes from this random sampling from this R, from this bootstrapping process.
Yeah, but you have the whole sequence, so you could, I guess, you could calculate the autocorrelation function of the.
Yeah, we have that. So let's see the. That's not here. Indeed, I mean, you can also compute these kinds of sort of distributions and autocorrelations of this R quantity. Yeah.
That would be interesting.
Yeah, so we've done it for other examples. Yeah, yeah. It's I mean, usually that's a good fit. It's good to know that you find it interesting, because for me, what counts is the X, it's the state, because that's what we want to simulate. But if you say, well, it's also the characteristics of that noise process are also
yeah,
relevant.
because I want to have a physical model, and I need to know the noise properties.
So you want the physical interpretation.
Yes, then I can do it on the computer, let's say, and I can try to reproduce this thing, but I need to know which correlations I get from the underlying dynamics.
Yeah, that's okay. So that's something I can't sort of state right away, because again, it's implicit. You can't come out of the bootstrapping.
But it would be very nice, because then you have the full physical model that you want to.
No, I understand that. Yeah. So I'm about to stop here. I mean, there's a bunch of more slides, but the main thing I want to say is I mentioned this cursor dimension, right? Because so we do all this by binning, right? So these elements in the feature vector, if you have too many there, the binning is not going to work anymore. So what can be done there? Well, if you want to sort of continue in this track of bootstrapping, so we turn around binning rather than binning the space of these feature vectors, right? So everything that goes into right, access of conditioning for this stochastic process, we can bin the output, right? So remember, this is what we want to do, right? When these feature vectors are closed, we get the next time updates, and we randomly sample from that set. Right? So instead of binning the space in which these feature vectors live, you can also bin the space in which these are at one time point quantities live. Okay, so the binning is the space in which these objects live. And because they're not distributed in time, right, the curse of dimension doesn't kick in as rapidly as it does if you bin the space of the feature vectors. Now, then of course you have a problem, because how do you know, right? So essentially you say, I have to sample from one of these, my R from one of these bins, but which one? And for that we need, anyway, a mapping, and we're going to train a neural net, this is what you can do, to map the feature vector that we have to the probability distribution of these bins, right? So it's this thing here. Given my current feature vector, what is the distribution, the probability distribution of these bins to find my next R in each of them? And it's a discrete probability distribution. So if you train a neural net for that, effectively that's a probabilistic classification problem, which is something that people have tackled with neural nets for quite some time. And this is not the most complicated task for machine learning. And so we do that with what's called a quantized softmax network. So I'm not going to go into the details of that because there's not time. Just show you one example from what's known as the Lorenz 96 model, test model for in atmospheric science. I'm going to skip right away to this thing here. So what we did here, this is for one element of the state vector of that system. This is the probability distribution. So in the pluses here, the black ones, are what the full model gives. In blue, this is what our sort of resampling parentization, stochastic parentization gives. This is the case where this feature vector consists of the current and last, so the current state and the 9 before that, right? So there's already some memory in there. Doesn't do a good job, as you see here. We can't capture that distribution well at all. But now, thanks to the fact that we turn around this binning and the fact that the machine learning, the neural net is able to capture that mapping, right, from the space of the feature vectors to this distribution of the bins, you can do that quite well. Here we get a good reproduction, right, of that distribution. And here our feature vector contains the last 75 time steps of the state vector. Right, we just added a very long memory here, right, and I mean mainly for demonstration purposes. Right, so this can really work with a fairly high-dimensional feature vector. Right, and we can still do this way of bootstrapping. Any other question? No. No. Okay. Sure. Okay, I'm run out of time already, so let me stop here.
Is it still now better because you got to use a longer memory, or you got a different method?
No, it's a longer memory because this is the same method, right? This is also with right. So with this memory depth of 9, right? It's also this QSN, the neural net that maps from the feature vector space to the bins. Right? So it's the same methods. There's okay. Now this is a case where you really need long memory, and we can do that. This is here you see the results. Okay, a little summary stuff that I showed. Let me just mention explicitly here the last point of what I've shown is this sort of machine learning assisted bootstrapping, resampling. Was nice, but there's still a lot more to do. In particular, the dimer example is something we haven't tackled with this machine learning assisted bootstrapping yet. So that's something we want to do. And more generally, machine learning for stochastic closures, it's natural to think, for instance, of neural stochastic differential equations or versions of that to pursue further. But there's still a lot of that needs to become there because it's right, for stochastic closure, again, there's just a lot less that has been developed so far. So then we want to do. Thanks. I'm going to stop here. Just show you the references with from which the various results come, and I'll be happy to take questions.
Thank you. Guess we're only have time for short questions. Please.
I was wondering, so basically you need a way to simulate things and then you try based on that to get your and this R, how you call it, the closure relation. But then that depends on the parameters, the physical parameters. So in a way it's not transferable.
That's a good point. I mean, so far, I mean, if you indeed, so these training data are generated under specific parameter conditions, and of course, then the question is, well, does it generalize to other parameter conditions, right? So that's a good point. And something on an open problem, I guess. Well, one thing you can think of is just enriching the data sets by producing data at different parameter values and adding that in the whole training procedure.
But then we have the power to simulate in more detail, then you don't need a closure relation anyway.
That's right. So it's true. I mean, this is very much about sort of reproducing what you can already do with the model that you have, right? So these reduced models, what would you use them for? Right? That's in a way what that relates to. So one thing is that you can generate very long time series. Right? People use model order reduction, for instance, in multi-query settings. They have to query their model many times over. That's one kind of thing that you can think of. Another is, and so I think, for instance, on the way parameterizations are used or developed in atmospheric modeling, but this right, so parameterization is made for a single vertical model column. Right, so if you can train that, right, and use a high resolution model just with the spatial extent of one of those boxes, you can train your process and then use duplicates of that. Copies of it in all your other model columns, right? And then that way you can meaningfully scale up to larger system and not just reproduce what you already have done.
I mean, you didn't last question.
Yeah, it's related actually. So your physically based model has parameters too, right? And you take them fixed and then you fit the neural net. But how sure are you about the parameters in the physically based model? Wouldn't it be better to also fit them? So to leave them open and to fit them in the neural net too. That might achieve an overall better fit than first fitting the first one and then the errors.
Okay, well, yeah, I guess it depends on what information you have available of those physical model parameters. Right? Do you have data for that, or is it more a matter of uncertainty propagation, right? Which are again other methods. So this is something I don't know. So I guess it depends a little bit on the particular problem, what it is you want to do with that.